In this lesson, I'm going to talk about double integrals over general regions in the XY plane. Okay, so really there's going to be two different types of regions, general regions that we're going to consider in the XY plane. And so let me draw the first type. So the first type, referred to as type 1, looks like the following. Okay, I'm going to draw this region in the first quadrant, even though it doesn't have to be. Okay, so if we just go back to doing double integrals over rectangles, the thing that was nice about a rectangle is that it has a nice boundary to it. Okay, it's got these two vertical line segments that form half of the boundary, and then two horizontal line segments that form the other half. Okay, so these two different types of regions are sort of going to take half of that scenario. Okay, so for example, for type 1 regions, think about the two vertical line segments that form the boundary of a rectangle. If we at least have that much, we have what's called a type 1 region. Okay, so a type 1 region, one example looks like this. So you'll see that the way this is formed, there are these line segments, these vertical line segments that form boundaries on the left and on the right. Okay, and but the other parts of the boundary are these curves. And the thing that is nice about these curves is that each of these curves can be considered to be y as a function of x. Okay, so this bottom curve that forms the boundary on the bottom, I mean, it's a curve that we can define in principle as a function of x. So I'm going to label it as g1 of x. And then this curve that is the bound above, it can also be in principle defined as a function of x. So I'm going to call that g2. Okay, so this is a type 1 region. And one thing that we can do with this type 1 region is that we can define it using set builder notation. It's the set of all points xy in the xy plane such that, all right, so such that any point in this region D, okay, the x component is between A and B. So that's one of the properties that we can list here. And then the other property is that the y component of any point in the region D is basically bounded by these two functions of x. So this is how we can define this set, this planar region, okay, using set builder notation. Okay, this planar region that I'm saying is what we call type 1. Some other terminology that's used for type 1 is to call it vertically simple. And I like that terminology because it reminds me that the boundaries that are nice here are these two vertical line segments. And when we go to set up our iterated integral, we are going to be integrating vertically first. Okay, so this is a type 1 region. We also have type 2 region. Okay, so for a type 2 region, so now we're taking, remember I said, these type 1 and type 2 regions are kind of like having half of those conditions of a rectangle. Okay, so the type 1 region, we had two vertical line segments as forming boundaries, parts of the boundary. For the type 2 region, we have two horizontal line segments forming part of the boundary. So something that would look like this. And then the other part of the boundary is a curvy curve where those curves, in this case for type 2, we could define x as a function of y. Okay, so for this curve, I'm going to call that curve h1 of y, and this curve here, I'm going to call that h2 of y. Okay, and for the y-axis, I can write in some labels. I can say that this is D up here, and this is C. Okay? And I can use set builder notation for this set, where this is the set of all points x, y, such that In this case, all the points in this region D, the y components are bounded between the constants C and D, and the x components are bounded between these two functions of y, h1 of y below and h2 of y above. Okay. All right, so these are the two regions, and type 2 region can also be called horizontally simple. And I like this terminology because it reminds me that we are first going to integrate horizontally when we convert our double integral to an iterated integral. So speaking of those conversions, let's write down how we convert a double integral to an iterated integral for each of these two cases. So for type 1, we're going to take our double integral over the region D of f of x, y, and we are going to convert it to an iterated integral where this set builder notation is kind of a guide to how you should set up the limits of integration, okay? Limits of integration on the outside, they will always be constant regardless of the kind of region we're considering, okay? So they're going to be A and B. And then the inside limits of integration, well, they need to be functions of just one variable, and in this case for type 1, they're going to be functions of x only, okay? And then we have our function of x and y, and we are going to integrate with respect to y first, or vertically first, and then with respect to x. And then for the type 2 region, we convert our double integral of f of x, y to an iterated integral where if you follow the set builder notation for the type 2 case, we're going to integrate from C to D on the outside, and then on the inside from h1 of y to h2 of y. Okay? And we are just now switching that order of integration so that we integrate with respect to x first, and then with respect to y. Okay? So this is what we do in general. Now let's take a look at an example. Okay, so the problem we're going to look at is this one here. So we're going to find the volume below the plane, z equals 3x plus 2y, and above the triangle that's bounded by the coordinate axes and the line x plus y equals 1. Okay, so we know that whenever we have a function that is always positive or non-negative, that when we compute a double integral, that we are actually computing volume under a surface. Okay. The first thing to do in pretty much any of these problems is to sketch the region of integration. Okay, so we're going to sketch this triangle that is forming the boundary in our xy plane. So we have our coordinate axes here, all right, and the line x plus y equals 1. Well, there are 2 points on that line, here and here, point 1, 0 and 0, 1. And I can just connect those 2 points with this line here. And so you can see that this triangle that's in the xy plane is just this triangle here. Okay. And so I can label my x-axis, my y-axis. Okay. And then I can label this as, I can label it for now as the line x plus y equals 1. Right? All right. And so now let's think about whether this region is type 1, whether it's type 2, whether it's both. It turns out that a triangle that looks like this is both type 1 and type 2, okay? And if it's type 1, we normally will prefer to set up an integral where we consider this as a type 1 region. So as a type 1 region, we want to convert our double integral, which is going to be computing volume. Okay, since this plane 3x plus 2y, as a function, it's always positive over this triangle, so we are computing volume. Right. So now to convert this to an iterated integral as a type 1 region, so we have our outside limits of integration. So our x ranges between x equals 0. So that's the left boundary, which is this line segment here. Okay. And notice that the right boundary is not a line segment, it's just a point, but that's perfectly fine. Okay. And so x, as you can see, ranges between 0 and 1. Right. Now for y, now we have to think of functions of x that form the boundary of our region. Okay. And so here is the lower boundary of that region, and it's simply the x-axis. And the way to describe the x-axis is y equals 0. So our lower limit of integration is just 0. Okay. And as far as the upper limit of integration is concerned, we need to think of, so here is our upper limit, okay? And we want this upper limit to be y as a function of x. And so I can rearrange this form of the line to subtract x from both sides. I can describe this line segment as y equals 1 minus x. So this is the curve that forms the upper bound for our y variable. Okay, so those are the limits of integration. And our function is 3x plus 2y. Doing this as a type 1 region, so you're integrating vertically first, that is with respect to y, and then with respect to x. Okay, all right. So now we find an antiderivative of the integrand with respect to y. So for this first term, the antiderivative of 3x is just 3xy. The 3x is constant with respect to y. And then for this 2y term, it is y squared. So this is our antiderivative, and we set up to do fundamental theorem of calculus. Right? And now we plug in 1 minus x in for y. So we get 3x times 1 minus x, and then plus 1 minus x quantity squared. Okay, that's if we plug in 1 minus x in for y. If we plug 0 in for y, we're going to get 0. Okay, so I can just cut off things here. I'll put square brackets. Okay, and so we're left with this single integral that if we do some algebra, we can simplify what's inside. Okay, and if you simplify, if you grind through and do the algebra, the integrand becomes minus 2x squared plus x plus 1. Okay. So now this is our single integral that we find antiderivatives for, and to finish off the computation. So the antiderivative of the minus 2x squared, that's minus 2/3 x cubed, and then we get a plus 1/2 x squared, and then a plus x. Limits of integration are 0 and 1. And then again, if we plug in 0, we get 0. If we plug in 1, well, we just get minus 2/3 plus 1/2 plus 1, and then simplifying all of that should be 5 cents. Okay. All right. So I'll state here as an exercise for you is to redo this problem. Redo it as a type